Today we're going to learn about properties of logarithms. This is page 1 of section 8.5. So, definition of a logarithmic function. Excuse me. Sorry. If x and b are positive real numbers, and remember b can't be 1, we learned, because when we have an exponential, remember how we do loop and swoop, and we can't have 1 to the something, because 1 to anything is 1, and that's a straight line. It wouldn't be the log curve. So the base can't be 1. X has to be a positive real number. So our argument we learned cannot be 0, can be any positive real number. So base has to be positive, but can't be 1. And x has to be positive. Then we learned that you can turn the logarithm around. Log base b of x equals y. And in the last section, we learned about loop and swoop. So base b raised to the yth power is equal to the argument x. So that's a definition of a logarithmic function. As I said in the last section, a log is just an exponent, because see what y is? Y is the exponent. So if anybody asks you what a log is, you just say it's an exponent. So the log of 1, no matter what the base is, the base could be 5, it could be a half, it could be 7, no matter what the base is, the log of 1 is 0. And if you ever forget it, because sometimes students go back and forth. Here, let me clean the screen so it doesn't look so bad. Sometimes students go back and forth and go, oh, is the log of 1 1 or is the log of 1 0? And I tell them, well, your calculator will tell you, so just do it. So type in log of 1, close your parentheses, and you can see it is 0. The reason why is because b to the 0th is 1. Remember how we learned in chapter 4, anything raised to the 0th power is 1. So b to the 0th is 1. And we learned in the last section, 8.4, that whenever the base of the log and the base of the exponent are the same, the answer is the exponent. And if there's not an exponent there, that means there's an imaginary 1 up there. So the answer is 1. And we can prove it by saying b to the first is b, which is a true statement. Anything to the first power is itself. And then same property as here. Remember, we learned these are called the inverse. Was it inverse? Ooh, I'll have to look that up for sure. I think it's called inverse properties of logarithms. I'll look it up before the next video and make sure I have that right. Property of logs. Because exponents and logs are inverses of each other, so they undo each other, and that's why we say, okay, if the base of the log is b and the base of the exponent b, then the answer is the exponent, which is p. And the reason why, b to the p equals b to the p, which is a true statement. And here we have the same scenario. The exponential has a base of b, the log has a base of b, so this time the answer is the argument, which is x. And log b to the x equals log b to the x. That's if we took both sides log base b. So those are our 3 inverse properties. So use the properties of logarithms to simplify the expression. Assume that all variables within the logarithms represent positive real numbers. So you should be able to do this without a calculator, and in the next class they do make you do it without a calculator. So here the base of the log is 4, the base of the exponent is 4, so they undo each other, so my answer is just the exponent, which is x, plus the log of 1 we said above is 0. So x plus 0 is just x. So like I said, no calculator needed on these. Here we have the base of the log is 3, the base of the exponent is 3. So my answer is the exponent, which isn't there, so I can assume that's a 1. Minus, same scenario, the base of the log is b, the base of the exponent is b, so the answer is just the exponent, which is 3. 1 minus 3, -2. See, these are fun, huh? And another inverse property, the base of the exponent's 5, the base of the log is 5, so the answer will be the argument, which is 7, minus the base of the log is 7, the base of the exponent is 7, so the answer will be the exponent, which is not there, so we can assume it's a 1. So this just equals 6. So all applications of the inverse properties of logarithms, and that is correct. For a minute there, I was like, wait, do I have that right? Yes, it is the inverse properties of logarithms. I don't think our book calls it that, but most textbooks do, so I want you to know the name of it by how you'll probably see it next semester. Okay, so we're going to add in some new logarithm properties here. So these are the ones we just talked about above. Log of 1 is always 0. These bases are the same, so the answer is the exponent. Bases are the same, so the answer is the exponent. Bases are the same, so the answer is the argument. So those are the same 4 that were above. And then we're going to add in 3 more. And you'll see pretty much the rest of the chapter revolves around these 3. So this is pretty big stuff. Logarithms are the inverse of the exponential function, as we said, so they share a lot of the same properties. So think about, this is multiplication. In multiplication with exponents, do you all remember that we add the exponents? So we get x to the 5th. Well, because the exponential and the log are inverses, the same holds true for logs. The log of a product tells you to add each of the logarithms. So log base b of x plus log base b of y. So it follows the exact same rule of exponents. In multiplication, we add our exponents. When the argument is multiplied, we add the logs. So they're inverse properties, and like I said, they share a lot of the same rules. So here we have log base b x over y. So let's think back. What did we used to do in chapter 4 with our exponents? Well, in division, we keep the base and subtract the exponents. So guess what? When you have the log of a quotient, you subtract the logs. And order is important in subtraction. So it's log of the numerator minus log of the denominator. So keep it in the same order as the problem. So division turns into a subtraction of logarithms. So the log of a quotient turns into the difference of the logs. Just like they did here, we subtracted with exponents. So anytime you're trying to think of a log property, think of an exponent property, and they share. This one, I don't really think there is a property of exponents like this, but this one's pretty easy to remember. Whenever you have an exponent up there, you just bring it down in front and multiply it by the log. So that's called the power rule. So these match. This was the product rule for exponents. This is the product rule for logs. This is the quotient rule for exponents. This is the quotient rule for logs. This is the power rule that just says any power that's out there, you can bring it down in front and multiply it by the log. And so we use these when we are solving logarithmic equations, rewriting logs, writing as a single log, expanding logs. So like I said, you will see actually all of these, but specifically these 3 a lot the rest of the chapter. Okay, let's go ahead and move on to page 2. So the first way we're going to use our new properties is expanding logarithmic expressions. So write the expression as a sum or difference of logs using the x, y, and z. Assume all the variables represent positive real numbers, which we need that to be true because these are all part of the argument, so we can assume that each of the variables is positive. So this is how we are going to use our properties. So does everybody agree this is multiplication? Right? So on the other page, or think about exponent rules, in multiplication we add our exponents. So when the log's argument is multiplied, we add the log. So this turns into log base 5 of 3 plus log base 5 of x. And you just do one piece at a time. So start with the numerator, multiplication turned into addition. Then we have division. Think of exponents. In division, we subtract our exponents. So in division, when the log has division in its argument, we subtract the log. So then we go minus log base 5 square root y. So let's take a look at this and make sure everybody's on the same page. So log base 5 multiplication turns into addition. So 3 plus log base 5x. And then division turns into subtraction. So we do minus log base 5 square root y. But you might remember in one of the last videos that I said we rarely keep radicals in our arguments. We usually change them to exponents. So do you remember from, what is it, chapter 6, that we learned that this is the same thing as this because it's power over index. So that is the same thing as y to the 1/2. So we rewrite that. But now we have the power rule. So once we have that 1/2 there, then we bring it down in front, which is the last rule we learned on the front page that said if you have a power, you bring it out in front and multiply it by your log. So we have a power, so we bring it down in front and it gets multiplied by the log base 5 of y. So that's how we're first going to use our powers, by expanding, then we're going to condense, and then we're going to actually solve logarithms and use these same things. Okay. So this first one's very similar to that one. So let's go ahead and try it. So how about we try A together, then you can turn off your recording and try B by yourself. Okay, so first thing I notice is that there's multiplication up here, and I like to put that in because sometimes that doesn't just jump out at students as 3x is 3 times x. So without looking at the denominator, we're going to take care of the numerator. So multiplication, think of exponents. In multiplication, we add the exponents. So the log of a product means add the logs. So this would be log base 4, 3 plus log base 4 x. And then division, think of division of exponents. We subtract the exponents. So when the argument has division, we subtract the log. So we do minus log base 4, 64. Okay, so now we have to look for simplifying, because it does say simplify as much as possible. 4 to the what is 3? No, 4 to the nothing's 3. This has a variable in it, so we can ignore it. But this can be simplified because 64 is a power of 4. It's 4 times 4 times 4. 4 times 4 is 16 times 4 is 64. So I'm going to finish that on the next